Okay, yeah, while he's preparing his presentation, let me introduce next speaker. Professor Hua Wang. The next speaker is Professor Hua Wang. He is the chair of the electronics at the Department of Information Technology and Electrical Engineering of ETH Zurich in Switzerland. Prior to joining ETH, he was with the Georgia Institute of Technology, USA. And before that, he worked at Intel Corporation and Skyworks Solutions. And he received his PhD degree from California Institute of Technology. And his research interests include innovating analog RF millimeter wave and photonics integrated circuits and hybrid systems for wireless communication, sensing, and bioelectronics applications. Dr. Wang is an IEEE fellow, and he received many awards, including DARPA Director's Fellowship Award, and DARPA Young Faculty Award, and the U.S. National Science Foundation Career Award. Okay, yeah, so please welcome Professor Wang.
Thank you. Yeah, I guess if I just talk and without can you hear me? Yeah. Okay. Great. Yeah. All right. Thank you, Professor Yu, and for your kind introduction. Good morning, everyone. My great pleasure to be here and deliver my Circuit Insight talk at the A-SSCC and 2024. And thank you for the invitation, and also thank you for the SSCS sponsorship of this event. Yeah. So I guess, and after Ali's talk, and we all learn a lot about the noise and the distortion. I really liked the way he introduced the noise in a very fundamental way, without using noise figures, noise temperature, but still we get a good understanding of noise. Now here, let's try to see whether we can have also kind of a grasp of the understanding on power amplifiers, RF power amplifiers, without going to the Volterra series, okay? So let's try to stay fundamental. And I also want to say that, I guess probably that's the reason I'm here. I want to introduce and at the educational level on this concept of waveform engineering. I want to emphasize that this is one or another actually fundamental concepts in the circuit designs, and not only applicable for power amplifiers, but also widely used for VCO designs, multipliers, and even DC to DC converters. Okay, so now let's get started. Well, this page is on my self-introduction, so I think Professor Yu already introduced me, so I will skip this one. Let's go to the outline of my talk. I will begin with the background introduction, kind of first introducing the concept of power amplifiers and why it is so important. Almost in almost all the wireless systems, so we need power amplifiers, and we really care about their energy efficiency, output power levels, and the linearity. And then I would like to introduce some basic concept of a power amplifier operations, right? So how do we evaluate a power amplifier? What are the major performance metrics we care about for a power amplifier? And what even more importantly, what really sets power amplifiers apart from general normal amplifiers we learn and day in, day out from textbooks, right? Why they are so special, and what are the new concepts actually make them stand out? And after that, I would like to introduce several popular power amplifier classes, and in particular, their waveforming techniques to play with their current and the voltage waveforms so that we can achieve better and better efficiency. So I will cover two types of power amplifiers, the linear power amplifiers, so class A, B, and C, as well as J power amplifiers. And then we will also look at the switching power amplifiers for the class F, F inverse, and the class D and the power amplifiers. And then the summary will conclude my talk. Okay, let's start with the background and the introduction. So power amplifiers is essentially, if we look at a wireless system, it is the last active circuit stage of a wireless transmitter. Essentially, it is serving as an interfacing circuit, bridging between antennas, and sometimes we can say TR switches, but the front-end antennas, and with the rest of the transmitter systems. So it is very important. And the power amplifiers are ubiquitously used in almost all the wireless systems, including mobile devices, access points, base stations, backhauls, and automotive radar and imaging, and nowadays, a very a popular and technology direction applications for the satellite communications. Right, power amplifiers are being widely used in all of these applications. So, well, as an education talk, let's start from the very fundamentals. So, what is a power amplifier? Right, as I said. Especially when an amplifier should be called a power amplifier. This really depends on the power level it is generating, right? Do we need to say that, okay, only amplifiers that can generate what level of powers are considered a power amplifiers? Or shall we say, maybe power amplifiers are kind of such a special class of amplifiers that the designers, we should not follow conventional design methods such as conjugate matching, right? So if that's the case, what are the new guidelines we should follow? Or maybe we should say that power amplifiers are very special because, hey, their operations will experience or typically require a lot of distortions or nonlinearities, right? Or maybe this is kind of my favorite, is that power amplifiers are special because if you don't use them properly, they can literally cause damages to itself or to something else, right? Okay, because of the high power operation. Well, loosely speaking, right, and the power amplifiers, we can show that, this is the general topology of power amplifier, right, very general, 2 stages, and with the input network, interstage matching network, and output matching network, right, we have driver stage and also power amplifier stage. So, loosely speaking, a power amplifier design can be divided into active circuit designs and the passive network designs, right? Both parts are extremely important. They have to be considered and jointly to achieve good performance of power amplifier. So the active circuit designs includes the device gain, efficiency, linearity considerations, and the operation modes and the classes, and the harmonics and the waveform shapings, and these are the 2 topics we'll really cover today. And there are also other considerations such as stabilities and reliabilities. Often they will pose additional constraints of the design of power amplifiers. And for the matching network designs, passive network designs, this is dealing with all these impedance transformations, power combining, and also helps with harmonic waveform shapings. Many of the assumptions we are taking today will eventually be achieved by the designs of those passive networks, right, in practice. And of course, the passive networks will also determine the bandwidth and often any other filtering functions of the power amplifiers. Okay, so let's look at the basic and some basic and performance metrics and the values on a power amplifiers. And these are the values we typically use to characterize the performance of a power amplifier, right? So again, let's use this general 2-stage power amplifier and circuit and define some of the quantities here, right? First of all, let's define several power levels. And with this power amplifier, and we have a certain RF input power, we call the P-in, and at the output of the power amplifier active circuit stage, okay, before the passive network, we call the output power from the PA directly as a PPA, and through the output matching network, and the actual power delivered to the load, and we call it the P out and or let's say PL, all right, and the power to the load. And of course, the amplifier is being supplied by some DC power, and we call the total DC power as the DC power drawn by the PA stage and the DC power drawn by the driver stage. The combination of the 2 is called PDC. And then now we can also define a power gain of the power amplifier, and which is basically P out, the actual power to the load, divided by the RF power at the very input, right? And this is here is in the linear scale. Of course, often people use in the dB scale, right? You use 10 log to describe the power gain. And we also really care about energy efficiency, as we know. So typically, there are two definitions of efficiency and values. The first one is something called the drain efficiency. So the drain efficiency of the PA is essentially the power delivered to the load divided by the total DC power consumption. And the PAE is called power added efficiency, further considers the fact that we also need to have a substantial driving power into the PA, so therefore we need to subtract that out. And that is therefore PAE is defined as P out minus your P in driving power and then divide by the PDC, right? Okay, so now let's run some numbers and to see and essentially this will give you a very intuitive understanding about why power amplifiers are so important, especially why their efficiency is so important. So now let's again consider this basic two-stage power amplifier, right? And we know the definition of drain efficiency equals output power to the load divided by the total DC power consumption, right? That's the definition. And now let's use some typical numbers, right? For let's say gigahertz RF power amplifier or lower millimeter wave frequency power amplifier at the peak efficiency maybe around 40%, right? Let's say 40%. And also let's assume the output power I want to deliver to the load is 30 dBm, right? And then in the linear scale is 1 watt. 1 watt of power delivered to the load. And then right away, we can calculate how much DC power this amplifier needs to draw from the supplies, right? So basically, that is 2.5 watt, right? And this is interesting because it draws 2.5 watt from the supply. However, only 1 watt is delivered to the load, right? And due to the conservation of energy, we know there's another 1.5 watt going somewhere else. The only place for it to go is heat. So as you can see that this power amplifier will generate 1.5 watt as the heat. Right? This really shows you the importance of PA design and why it is so critical to couple the power amplifier design together with thermal management, and it will have direct impact on the battery life and so on and so forth. And further, let's say we want to supply this power and DC power by 2.5 volt power supply, and this means that the total DC current from the supply will be 1 amp. Right? This is a huge DC current drawn from the supply, and of course it leads to typical very large IR drop and the reliability considerations for all the design aspects. Right, let's consider further. Now, let's consider the network loss at the output, right? And we know that in practice will be some kind of loss. And with a very simple derivation, we'll see that, hey, the drain efficiency of a power amplifier in this case is essentially P out over PDC, right? Power delivered to load. And we know power delivered to the load is just the power from the device times the loss factor, whatever loss we have, divided by PDC, right? Then let's also assume, and the loss is only 1 dB, let's say 80%, right? This typically is the value of a very low loss and on-chip matching network, maybe including some bump and some a little bit additional package loss. Right? This is actually very low loss already. And with that number, we can show that, hey, the output power and from the power amplifier, right, it actually equals, and the basically efficiency from the PA itself before having the loss needs to be 50%. This further imposes the challenge of the design of PA. The core needs to be 50% of efficiency. And moreover, if I have 1 watt of power, right, and the loss of the matching network is 1 dB and 80%, and we can see that, hey, the power delivered from the PA need to be 1.25 watt, right? And if you look at the difference of these two numbers, this essentially means 250 milliwatt of power will just be lost and in this output matching network, right? Other than the reliability thermal considerations of that, we also need to recognize this is a lot of power and power waste, right? Typically, this is even more than a power of typical receiver, entire receiver and the power consumption. So again, this shows that it's very, very important and for the PA design, and especially managing its efficiency and its loss. Finally, let's look at the power gain, right? The definition of the power gain is the total power delivered to the load divided by the power into the PA. And let's say, let's assume the power gain is 20 dB. This is also a very typical number. and for gigahertz or even low millimeter wave power amplifier designs, right? And because typically if we go higher number than this power and the gain, the PA you need to be more careful about stability. But let's say 20 dB power gain, right? And the delivered power to be 30 dBm. That essentially means my input power need to be 30 dBm minus 20 dB, which is 10 dBm, right? And it is 10 milliwatt. And but we should also recognize that 10 milliwatt driving power is a lot of power, right? And that this is something need to be achieved by an up conversion mixer, right? It's actually, or maybe sometimes we need to have another stage of the driver, and then overall efficiency will degrade further. Okay, so as we mentioned, efficiency is extremely important for power amplifier. Why? Because the total power consumption is very large. Right? Any small improvement in efficiency will have a large impact at the overall system. Okay, so there are some fundamental limits, or let's say fundamental factors that determines the efficiency of a power amplifier. Right? And if we reference the Professor Peter Aspect's paper from 2019 and a nice review paper, it can be shown that the power amplifier efficiency is determined by efficiency of the device itself, efficiency due to the power amplifier operation modes, classes, harmonic shaping, termination, which essentially is the waveform engineering that will be really covered for the later part of my lecture. And the efficiency is also determined by the power gain, output matching network loss, and also the thermal and aging of the device. Again, for the focus of this talk, we will look at power amplifier classes and harmonic shaping and termination techniques that will come in and govern this efficiency and the factor. All right, so when we are talking about power amplifier classes and different modes, and here is a summary table and for most popular classes and their general properties. There are many other classes, and we will not have the scope to cover them, but these are at least the very popular ones. So first of all, and as I said earlier, the power amplifier classes or modes are loosely defined as linear mode and the switching mode PAs. Okay, for the linear mode PAs, we'll emphasize them first, and in the next few slides, and it starts with Class A power amplifier, and then getting to the Class B power amplifier, Class AB power amplifier, and the Class C power amplifier. Later on, we'll see that hey, they are almost the same circuit, right? And the topology is exactly the same. The only difference among those power amplifiers are essentially their conduction angles, right? So what's the percentage time they will be on through the entire the RF signal cycle, right? And then we'll look at that. And then we will see that, hey, there are different type of linear power amplifiers and actually using non-zero harmonic terminations, and that can lead to interesting properties too. And then I will introduce the Class J and the Class J star power amplifier and in my following talk. Okay, but anyhow, for these linear mode PAs, and the transistors are operating more like current sources, right? And they have good linearity, and they will offer medium to sometimes low drain efficiency, and as a trade-off with their good linearity. And they can amplify complex modulations with varying amplitudes such as QAM and other more advanced modulations. And they typically will harmonic suppressions, but sometimes they use a certain level of harmonics at a good right and the phase and amplitudes to perform and further waveform shaping, like Class J PAs. And they typically will have large power gain, which is very nice, which is a very nice property, and they can operate towards higher operating frequency. Right? If you look at higher millimeter wave PAs, and they are exclusively actually using the linear mode PAs. And there's this signal type of big classes of PAs like switching mode PAs. Right? For example, Class D inverse, and the Class E power amplifiers. And in contrast, for those type of PAs, the devices are typically used as RF switches, and the on or off, right? They don't have very good linearity, But they can provide very high drain efficiency, theoretically 100%, right, with lossless passive network. And we can also see that, hey, because of their limited linearity, typically they are being used for constant amplitude modulations, but additional techniques can be added to them so that we can amplify linear modulation and varying amplitude modulations, which is, of course, a little bit beyond the scope of this talk, but it can be used in that way too. And they exclusively also rely on waveform shaping as well. But typically, because those devices are used as RF switches, we need to turn them on and off pretty hard. So therefore, their effective RF gain, power gain, will be a little bit lower because we have to drive them really hard. And then they are more applicable for lower or medium frequency or operating frequency. Right. There's this class F and class F inverse power amplifier sitting somewhere in the middle. Some of the textbook will introduce them as switching mode PAs. Some of the textbook will introduce them as overdriven harmonic-shaped linear mode PAs. Right, so it's very interesting, but we will also look at the class F and class F inverse mode PA in this talk as well. All right, so now let's get started with this power amplifier and analysis. Right, first of all, we need to define the power device model. Right, we can go, as I said, and a very complex way to represent and a complete way to represent the power device models all the way to Volterra series, but often, and that's not the best way as a beginner and to study in this area. Better we use some simplified model so that we can grasp almost most of the properties, but at the same time without losing circuit insights, right? Which is the thing we want to emphasize here. Okay, so if we look at simplified device model for power amplifier designs, and first of all, we assume, right, the device is connected in the common source configuration. Right, there are different other configurations too, but here let's just assume it's in the common source configuration, right? And they behave as an ideal voltage control current source and VCCS. And further, and the device is because it's the ideal voltage control current source, so we ignore its output impedance, right? And this is infinity, and the device will never go to triode region. Okay, of course, and the output voltage will swing all the way to 0 volt, but not below. Okay, and further, the device will not have any subthreshold region. So in the sense that it can be abruptly and turned on or off right away. Right, and once the device is on, in the sense that the VGS, your drain source voltage, is higher than your VTH, and then the output current is completely linear. Linear in the sense that output current is directly proportional, linearly proportional to your overdrive voltage. Right? This is also the assumption. All the way to some maximum current that can be supported by the device. We define that current as ID peak, right? The peak value of the drain current. And further, and for the power amplifier analysis, right, we also need to put the physical parameters on the output voltage. Typically, there is a hard limit on the output voltage as well. And in a lot of power amplifier designs, I will show you very soon, this limit is set as a 2 VDD. Right? And I'll explain why it's 2 VDD. So therefore, from output current, drain current, and the drain voltage perspective, and you can see that, hey, we will have this a rectangular space, and the voltage from 0 to 2 VDD, and the current from 0 to ID peak. Right? So you can have sine wave or waves with forms with harmonic shapings, but has to be within this rectangle, right? Cannot go beyond. Otherwise, the device will have reliability concerns. Okay, so this is a simplified model, but it's quite useful for and all the linear PA analysis and most of even the switching PA analysis too. All right, so moving forward, when we are talking about the power amplifier designs, right? What's really special about it? And I besides the high output power and the consumptions, or let's say the capabilities, I believe that this matching is also a very, very important and also basic concepts. And here, let me introduce two types of power matching here. And first of all is the conjugate matching. So the problem setup is given at the upper part of this slide. So let's say we have RF current source, right? And let's say it is generating a sine wave current coming out with amplitude of the current to be to be higher than 0, but less than something called we call Imax, right? Basically, it has this current generation capability of this current source. And this current source also has some source impedance, and we call it YS, right? Or let's say 1 over ZS source impedance. And then the power was supposed to be delivered to a load, and the load impedance is ZL, or let's say YL, okay, equals 1 over ZL. And of course, we know there's something called conjugate matching, right? The goal of conjugate matching is to maximize the power delivered to the load if the current has no voltage limitation. Right? So this is just essentially, let's say, hey, with this setting, I want to maximize my power delivered to load. So how do we do conjugate matching? We all learned that in the basic textbook, and we need to design the load to be complex conjugate of your source, right? So in this case, YL needs to be YS star or ZL equals ZS star, right? Maximum power transfer matching. And with this assumption, immediately we know that the maximum power delivered to the load will be 1 over 8 times Imax squared divided by real part of the YS. I use Y parameters because here we are dealing with current source. We prefer to use the Norton equivalent circuit. Okay, again, Imax is the amplitude of the sine wave here. All right, that's the conjugate matching. However, in practice, for power amplifier design, conjugate matchings are not really useful. We need to consider load line matching. Why? Because as I said, the current source, we cannot have unbounded voltage across the current source. Typically, it's also limited by its maximum voltage swing. And here we define the maximum voltage swing as Vmax. And of course, and then with this assumption, let's also assume it's a good enough current source, then in the sense that the source impedance will be much larger than the load impedance typically. And if we consider both the current limited condition and the voltage limited condition of the current source, it can be shown that the desired load is actually equals basically Y prime YL, real part of YL equals maximum of a current from the source, current source, divided by maximum voltage across the current source. And of course, in this case, we also need to have the reactive part cancel each other, right? And we only remaining real part. And with this condition, it can be shown that the maximum power delivered to load will be 1 over 2 times Imax times Vmax. Now let's see the significance here, right? And let's put some numbers in. Let's assume a current source, the maximum current will be 1 amp, and its own the load is 100 ohm. Let's ignore the reactive part, just only real part. The maximum voltage swing will be 2 volt of this current source. Now let's do conjugate matching. Pretty straightforward, and the load need to be the same as the source, need to be 100 ohm, right? We know that. And then you can easily show that the power to the load will be 12.5 watt, and at the maximum current of 1 amp from the current source. Why? Because if 100 ohm, 1 amp, then the RF current amplitude to the load will be 500 milliamp. And 500 milliamp and over 100 ohm, and it's 12.5 watt, right? Because 1 over 8 and the calculation. Okay, but the important thing to recognize that if I have 500 milliamp going through this 100 ohm resistor, this means the voltage across the current source will be 50 volt. This is way higher than the breakdown voltage of the device here, which we define as 2 volt. Therefore, it means this is not possible considering the voltage constraint. Now, if we further consider the voltage constraint here, 2 volt, and with the load to be 100 ohm, it just means, hey, I cannot generate so much current anymore. I have to back up. I have to back off a lot. And when we do the back off, it shows that the maximum current I can support and will be 40 milliamp from the source, then 20 milliamp to the load. And this will lead to only 20 milliwatt delivered to the load. Right? You can see this is actually the load line and the plot. The maximum, here is the voltage, here is the current. Remember, we have to stay below 2 volt of maximum voltage. So therefore, this triangle is the only power we can deliver in practice. And this big triangle is the theoretical value that can be achieved by conjugate matching. But again, we cannot get there. We have to stay within this rectangle. Now, further, and if we look at the load line matching, and and based on the previous and the derivation, the optimal load will no longer be 100 ohm. Rather, it is the ratio between the maximum voltage divided by maximum current, which will be 2 ohm in this case. Of course, it's much smaller than 100 ohm. That again shows that, yeah, this is a good enough current source, so all the assumptions are reasonable. And in this case, we can calculate that the total power will be 1 watt. Why 1 watt? Because it's 1 amp from the source. This is the 2 ohm. This is 100 ohm. Almost all the current goes to the 2 ohm, and you can calculate the power will be 1 watt. Right? You need to time another 1/2 because of this amplitude of the RF current here. And this is actually the load line and the curve for this scenario. Right? You can see that it fully occupies the entire rectangle and give you the best power you can get. Right? So this is the load line condition. Of course, again, if we use conjugate way matching, and theoretically you can generate more power, but in practice, considering the two constraints, and we have to go with the load line matching. Right? Okay, how to achieve this 2 ohm and resistor? Well, this is essentially the topic of the impedance transformation. Yeah. Now, with all of this background knowledge, we are equipped to investigate different power amplifier classes and their waveform shaping techniques. First of all, let's start with the Class A power amplifier. Here is the circuit topology of Class A power amplifier. And you can see that, hey, I have a common source and a transistor. Let's say we use MOSFET, NMOS as an example. The input is applied at the gate, Vin, as a sine wave. And the drain of the device is connected with the choke to the VDD, right? So that we make sure that the DC voltage at the drain is biased, fixed at the VDD. And the output of the drain is connected with a DC blocking capacitor, right? It's just blocking. And the output further goes to the load, RL, right? And the typical assumption for this and the classic linear power amplifiers, we assume all the harmonics need to be shorted. So therefore, we put a harmonic trap here. This is the LC parallel resonance tank, and resonating exactly at RL. So therefore, at the frequency of F0. So therefore, at the frequency of F0, and this is an open circuit, right? And all the current will go through RL. But at any other harmonics, this will be a short circuit, so it will actually terminate, short out all the harmonics. So now with this basic circuit, and with all these assumptions of the power devices, we can look at the output waveforms of this circuit. First of all, let's look at the input voltage, right? And it's a sine wave, and it's Class A power amplifier, so therefore the assumption that it is being driven above the threshold voltage, okay? So it's always on, device is always on. Now, let's look at the output current. Of course, it sits around the DC current, right? And remember, the current needs to be, when the device is on, is a complete linear device. So therefore, the output current will also be exactly the same sine wave as as your input DC drive. Okay, that's a current. And in this case, and because the ID and the IL, and when they sum together, and they equals the IDC. IDC equals ID plus IL. So therefore, the IL must, first of all, IL has to be an RF current, cannot be DC current, because it's being blocked by the DC capacitor. And further, the phase of the IL as a sine wave have to be the inverse value of the ID, because they have to cancel each other, so that their summation is a DC current, right? So therefore, IL need to be a sine wave, number one, and has to be in reverse the phase of ID. So it's this sine wave, okay? This IL is going through a resistor, RL, so therefore, the voltage across this RL, just simply this also same sine wave in the same phase. And again, because this is the blocking capacitor, so whatever voltage showing at the VL as the RF voltage needs to be the same as the VD, right? Otherwise, you will have infinite current and through this short circuit. So these two voltage have to be the same for the RF voltage. So therefore, whatever VL you have here has to be mapped at your VDD, at the VD. And further, the VD, the DC value of the VD need to be VDD. Now, this is essentially the basic operation of the Class A power amplifier waveform. Now further, we will look at this waveform. Let's start to increase the input drive, right? So still maintain as a class A, and we can increase the input voltage drive all the way to essentially touching the VTH, right? The lower part touching the VTH. And in this case, and if my V in touch the VTH, that means my overdrive is 0. And again, remember, this is the device that can be turned on abruptly. So therefore, at that particular moment, your output current has to be 0, correct? It has to be like this, because the current is exactly linearly proportional to your overdrive voltage. And then we can imagine the current needs to be a sine wave and with this shape in red, right? And the touching exactly 0. Now further, the same analysis, right? So basically your output load current needs to be the same sine wave, but with reversed phase, because addition of these two has to be a DC current, right? Coming from the choke, correct? Okay, so therefore the voltage across the load needs to be this shape, the current needs to be this shape, and correspondingly this has to be the voltage, and this voltage is mapped back to your supply and to a drain voltage, and it needs to be this shape. Now let's further look at the numbers. First of all, let's assume that in this case, my current exactly touching the peak, which I define as a maximum current generation by this transistor is ID peak. And what is if this is sine wave and the maximum the current is ID peak, then the RF current amplitude should be ID peak divided by 2. I define that value as I max, number 1. Number 2, the same RF current is going through the load. So therefore, the amplitude of the RF current going through the load is I max. Okay? And then now let's look at what's the maximum voltage I can achieve in this case. We know it's a sine wave of the voltage, right? We also know that the voltage at the drain has to sit around VDD. That's the DC voltage. So you go up and down. And we further know it's an ideal device, but the voltage cannot go to negative. So therefore, the maximum value we can go down is to 0, which means it's a sine wave voltage, but the maximum amplitude of sine wave has to be VDD. Correspondingly, the highest swing of your drain voltage need to be 2 VDD. Right? This is the only possible solution and the maximum voltage swing. And in this case, we know the RF voltage swing at the load is the same as RF voltage swing at the drain. So therefore, the load voltage swing is also VDD as a sine wave. Now, taking the difference of the two, you will have your optimum load, which is VDD divided by Imax. And further, the load and the output power at the load will be 1/2 times VDD times Imax, right? Okay. What about DC power consumption? This is pretty straightforward now, because the DC current equals Imax, and which is the amplitude is the same value as the RF current and of the sine wave, and the DC voltage is the VDD. So therefore, maximum DC power with VDD times Imax. Okay. And if you take the difference of take the ratio of the two, you can find what is the drain efficiency of the ideal class APA. Is drain PL divided by PDC. This equals this value divided by this value is 50%. So even with perfect waveform, lossless matching network, your efficiency is only 50%. Okay. And now let's further look at the backup efficiency of this amplifier, right? And we can see that when I amplify smaller signal, my output signal of course decreases, but my DC signal does not change, because my DC signal, the ID and IDC and the VDD do not change. So therefore, the VPDC is a constant value independent of the PL. And then as a result, my backup efficiency scales with the power to the load, or scale with the power to the input. Now let's look at the class B power amplifier. It's very different. And first of all, in the waveform, but actually the same as the circuit topology. You can see that this is circuit topology. It's exactly the same as the class A, right? But now we operate them differently. Rather than bias the V in to be high, we bias it exactly around the VTH, right? So you have this kind of waveform. All right, so you can see that half of the time the device is, the input voltage is below VTH, half of the time device input voltage is above VTH. So therefore, and we would expect half of the time device is off and half of the time device is on. When the device is on, it's a linear device. Remember, VCC, the voltage control current source. So therefore, when the device is on, the waveform has to be halfway rectified sine wave. right? That's the right solution. Okay, now that's my ID. And remember, my IL plus ID has to be IDC. So whatever the Fourier series fundamental component of the ID, the inverse phase of that has to be my IL, right? It has to be sine wave to the first order, but with inverse phase. And then the VL also is essentially RL going through a real voltage, a real resistor. Therefore, you have this voltage waveform, and the same VL will be mapped around VDD. Okay. Now, let's increase the input voltage drive. How much we can increase? Let's say we increase to the value that, hey, my ID, again, go to the ID peak, right, red one. And then all the voltage and current will increase correspondingly, right? But the important thing to recognize essentially all the numbers accordingly. So when my ID goes to ID peak, its RF components, interestingly, is still half of the value. So Imax, the RF component amplitude of this, equals Imax equals ID peak divided by 2. This is the same value as a class A power amplifier. But what about DC component of this ID? Well, you can just look at the Fourier series of the DC component of this half-wave rectified sine wave. Without going through the details, I can still tell you that it equals its ID peak divided by pi. So therefore, and also equals 2 times Imax divided by pi. And putting everything together, we can see that the maximum power delivered to the load equals 1/2 times VDD times Imax. And the optimal load equals the VDD, still divided by Imax, the same as the class A power amplifier. And the maximum DC power consumption in this case is different. The DC power consumption of this class BPA is DC voltage, which is still the same as VDD, and times the DC current of the drain current. The DC value of the drain current is 2/pi times Imax. Okay, and basically then we can look at the drain efficiency by using this PL divided by PDC. Now equals pi over 4. This is a value of 78.5%, which is much larger than 50% as a class APA. Right? So basically, you can see that, hey, first of all, class BPA has a much higher peak drain efficiency than the class APA, and further, the PDC is not a constant value. You can see the PDC really scale with the load power. If you have a higher power delivered to load, your DC current goes up, and correspondingly DC power goes down. And it actually deserves a further discussion of this backup efficiency. So if you look at the class A and the class B power amplifier, if I may summarize again, the class A power amplifier, their efficiency essentially is proportional to load divided by the DC current, right? Because the DC voltage is always a fixed value. And we know that the DC current of the class APA is independent of the power delivered to load. So therefore, is PL to the power of 0. It's nothing to do with PL. It's a constant value. And then you can see that the backup efficiency of class APA is proportional to its power delivered to load, and therefore proportional to power as the input, assuming the constant power gain, and proportional to the voltage square as the input. But the different thing is the class B power amplifier, right? And the efficiency is proportional to the load power delivered to the load divided by this DC current. The DC current is actually proportional to square root of its power delivered to load. Okay, why? Because it's proportional to its RF current, which is therefore the square root of the power delivered to load. And if you take the difference of 2, then this is proportional to the square root of the power delivered to load, then it's proportional to the square root of input power, or we can say linearly proportional to an input voltage drive. What's the significance of this? Right? We put all these math. What's the significance? The significance can be shown in these two plots. We can compare the normalized drain efficiency of class APA and class BPA for different power backup values. The difference and the figure on the left shows the backup power value in terms of dB, power backup. The figure on the right shows a power backup in terms of the voltage, input voltage versus the maximum voltage. First of all, you can see that, hey, at the 3 dB power backup from the power, the Class B PA and is substantially higher than Class A. It's actually 1 over square root, and but the Class A is 1 over 2. This is the difference. This is because the scale and proportional to the power and or for Class B, and then proportional to power square for the Class A PA. Okay, at the 6 dB power backoff, the Class B PA efficiency dropped to half of its peak value. The Class A PA drops to 1/4 of its value. It's very, very different. Similar thing can be shown in terms of amplitude. But don't forget, both of these PAs, they have very different peak efficiency. The Class A PA is 50%, Class B PA is 78.5%, right? So therefore, if we look at absolute value of their backoff efficiency, the Class A efficiency at the 6 dB power backoff, 1/4 of output power equals 0.25 because it scales, as I said, and with its power and the times delivered power times 50% peak efficiency, then equals 12.5%. But the Class B PA, in contrast, equals 39.25%. So you can see that it has a lot more advantage than Class A PA in a power backoff operation. And this is, and further, you want to improve the efficiency, backoff efficiency, we should go to more advanced architectures like Doherty out-facing, which is beyond the scope of this lecture. Now, we understand that the Class A PA and the Class B PA. Class AB and the Class C PA can be understood very easily. Essentially, for the Class AB PA, we just biased the input voltage DC-wise somewhere between Class A and the Class AB, right? So basically, therefore, their turning on time is larger than 50% of period, but less than full period. But on the other hand, the Class C PA, we bias the DC voltage is below the VTH, so therefore its turn on time is larger than 0, of course, but less than basically half of the period. Now we can summarize everything, and you can see that all the Class A, B, and B, and C, they can be placed in a unified framework. Essentially, we can use something called a conduction angle to describe their operation. For Class A, of course, the conduction angle will be 2 pi, Class B will be pi, and AB is somewhere between A and B, and C is below, basic conduction angle is below pi, right? And further, it can be theoretically derived, or the drain efficiency by Fourier series, and versus the conduction angle is given here. And the interesting observation is that, hey, basically, Class A at the RF current at the fundamental current at the fundamental frequency, Class A equals Class B and less than Class AB. And further, if we look at this equation and drain efficiency, and it has a potential to go to 100%, but at the expense of the conduction angle almost 0, essentially almost no power delivered to the load. So therefore, it's not a practical approach. Okay, so for the linear PA, we can also look at some very interesting properties and another different topology, the so-called Class J power amplifier. We are taking a very basic assumption that the linear PA, we have to have short termination. And the question is that really necessary, right? And to operate the class linear PA? Well, the answer is not necessary. This is really not necessary, right? For example, let's look at this circuit topology. It's a linear PA, but now we are using capacitive harmonic shaping. How it works? First of all, the PA is shown in this way, right? This is a common source amplifier, the same setting as we had before, but we have a capacitor at the output of the PA, of the device. And then the transistor has a series LC and a filter network, and then the drain of the device is connected with a choke to the supply. Okay, and in this case, let's also make an assumption that the device is operating in a Class B mode bias. So therefore, the drain current is only a half cosine wave, okay? And the sitting centered around 0, right? If we look at the conduction angle theta. And let's also only consider DC and the first order and the second order signals, right? You can see some basic circuit analysis in this case because it's a series LC resonance, so therefore only fundamental RF current can go through the load. And when this current goes through the load, and this is the DC current, then we can look at what is the corresponding ID and IC. And we know the ID has to be halfway rectified sine wave, so therefore IC equals DC current and a DC current plus this sine wave minus this half-wave rectified sine wave. And this current can be integrated, and then we can figure out what's the actual voltage across this capacitor. These are the details. But the important thing is to play with the harmonic shaping. If we look at the current and the Fourier series of the current, it can be shown in this way, right? Basically, this is the DC first order and the second order current. And we can have the DC current normalized to class B, we call it 1. And it's cosine theta. Why? Because it's even function. And also it has a second order, 1/2 cosine 2 theta. And what about the voltage? Right, there are a variety of voltage we can derive here. But let me just give a voltage expression equals 1 minus cosine theta minus sine theta plus 1/2 sine 2 theta. Why this is significant? First of all, the DC is 1. This is the same as a class B and the DC current, DC voltage. And the DC, the fundamental component of the DC, of the voltage, drain voltage, is cosine theta. So this is also the same as a class B fundamental voltage. And then I have this additional term of minus sine theta plus 1/2 sine 2 theta. It can be easily shown that these two inner products will generate no real power. And the inner product of these two also generate no real power. So therefore, the existence of these waveforms, of these signals, are only for the waveform shaping. This can be easily even shown here. See, the same drain current as I shown before. And as a matter of fact, my drain voltage can have a family of voltage waveforms with a coefficient of alpha here. Okay, it doesn't matter about this alpha. Can be basically as a scaled one, is larger than -1, smaller than 1, and we can further factor this out as this equation. But independent of alpha, and the inner product of these two will always be 0. It generates no real RF power. Okay. However, this transistor will consume the same DC power consumption as the class BPA, and also generate the same DC fundamental RF power as the class B power amplifier, right? So now we have a collection of power amplifier modes with non-short harmonic terminations, and you can see the voltage waveform can be plotted in this plot, right, versus the conduction angle. It can be shown that, hey, if alpha equals 0, essentially all those terms will go away, and this is just a class B power amplifier. And then if alpha equals 1, and this is essentially this solid blue curve, this is called class J power amplifier. If alpha equals -1, it's called class J star power amplifier. But regardless, you can see, and all of these class J star power amplifier will deliver exactly same RF power as a class BPA, and consume the same DC power consumption, therefore having the same drain efficiency, right? Again, this is all about the waveform shaping, right? Now this amplifier advantage is that it can accommodate different capacitors at the output load. What is the price to pay? Your voltage swing will be higher than 2 VDD, right? So that's the price to pay, which will affect to some extent your reliability. Finally, let me talk about the switching PAs. I need to really speed up my presentation and finish up the switching PA, and then hopefully I can still take some short questions. And why do we want to do switching PAs? We look at different class A, class AB, or these linear PAs. We know that, hey, there's a fundamental limit of the maximum drain efficiency we can achieve. Why is that? And you can revisit the class B PA waveforms. Now this is the waveform of the drain voltage. This is waveform of drain current. And we can also calculate the power wasted in the device. What's the power wasted in the device? And we look at the transient drain voltage waveform, multiply the transient drain current waveform, and do the integration and over T, and average over T. That is the power wasted in the device. So therefore, by inspection, we know that, hey, the more we have overlapping between the drain voltage and drain current, the more power consumption goes to the device itself, and the lower the efficiency it will be, right? This is the fundamental limits of this linear power amplifier efficiency. So therefore, and the designers are very smart. Hey, why don't we actually opt the device as a switches? Why it is useful? because in this case, if the device is a switch, if the switch is on, then it's an ideal short. That means it can conduct current, but there's no voltage across it, right? So no power. But if the switch is off, then it can withstand high voltage, but no current going through. Again, no power consumption. So ideal switch will not consume any power consumption. So therefore, if we can put together a circuit, a switching PA with ideal switches, hey, maybe perhaps we can get 100% of efficiency. Now, is this possible? Okay. The first example is so-called Class F power amplifier. This is the basic topology of Class F power amplifier. It can be understood as a switching PA or as an overdriven linear PA plus harmonic termination. In this particular lecture, let's just try to understand that as a switching PA. Okay, so this here I have a transistor with a choke to VDD, and I have a load resistor, and I have a parallel LC network for the harmonic termination. And then I also have this Lamellar 4 transmission line that is Lamellar 4 at the frequency, at the carrier frequency. Okay, the characteristic impedance of the line is also RL. All right. So what's the meaning of this open matching network? If we just look at RL in parallel with this LC tank, at the fundamental frequency, of course, it's RL. Why? Because this is the open circuit. At the signal harmonic is short. At the third harmonic is short. At all the harmonics and looking into here will be short because it's shorted by the LC tank. And interestingly, if we look at this Lamellar 4 transmission line, if we look at the load from the observed by the device at the fundamental frequency, and it is RL, because RL and this transmission RL, you see RL. And but at even order harmonic, and the impedance seen here is essentially the same replica impedance seen and on the other side of the transmission line. So therefore, it will be short and short. At the odd order harmonics, it will be impedance inversed. So therefore, your load will see a short circuit, but your device will see an open circuit. So it's open and open. Well, what's the significance here? Again, basic circuit theory, we know that short circuit can support current. Short circuit cannot support voltage. Open circuit can support voltage. Open circuit cannot support current. Therefore, if the load is short for all the even harmonics, that means the current going through the transistor has to be fundamental plus all the even harmonics. Cannot be anything else. And if the load is open for all the order harmonics, that means the device output voltage has to be fundamental plus all the order harmonics, right? So this has to be waveform. Now let's also assume that we have 50% duty cycle on and off of the device. What are the solutions? There's actually only one solution that is the realistic, right? So in this case, even see the current has to be 50% duty cycle, so 50% of time has to be 0. And then the rest of 50% is on. And the current can only contain even order harmonics and the fundamental. So therefore, the current has to be this half-wave rectified sine wave. What about the voltage? The voltage needs to sit around the VDD as being biased, and it has to be an odd harmonics. So therefore, around the VDD DC value. So therefore, it is square wave with 50% duty cycle. And because of square wave, it can go up to 2 VDD and it could go down to 0. Okay. Now here are some base and further calculation of a power and the optimal load. I will not have time to go through that, but interesting to recognize that what about the drain efficiency in this case? Just by simple observation, you can see that there's literally no overlapping between the drain current and the drain voltage. If you take the integration of the drain voltage, drain current over the time, it's 0. The transistor consumes 0 power. So therefore, based on conservation of energy, all the power from the DC will go to the load as our desired power. So therefore, theoretically, this PA can achieve 100% efficiency. Okay, as a duality is something called class F inverse power amplifier. The same topology is almost the same topology. The only difference is that instead of using a parallel resonance, we use a series LC resonance here. Okay, so that's the difference. Well, and with this series LC resonance, if we look at the load at this side of the transmission line to the load, we will see that, yeah, it's RL at the fundamental frequency, then it's open circuit for all the harmonics because of the LC series resonance. And now with this transmission line, so we know that, hey, the load seen by the transistor need to be RL at the fundamental frequency. And again, the transmission line number 4 at the fundamental frequency. So therefore, it will maps the impedance of the load at all the even order harmonics frequency to the transistor. So therefore, and the transistor will see open at the 2F0 and also open the 4F0. The Lamella 4 transmission line will give you impedance inversion at the odd order harmonic frequency. And so therefore, and if the load is open here, device will see short at the 3F0 and also 5F0. Now again, remember, basic circuit theory. The short circuit can support current, cannot support voltage. And the open circuit will support voltage, cannot support the current. So therefore, we can see that the load seeded by the transistor is open for all the even order harmonics and is short for all the odd order harmonics, right? So it means what? It means the current coming out of this transistor has to be fundamental current plus all the odd order harmonics of the current. The voltage of the transistor has to be fundamental current voltage plus all the even order harmonic voltage. And what are the solutions? Here is the solution. Assuming 50% duty cycle, there's only one solution. And the current has to be 50% square wave, and your voltage has to be half-wave rectified sine wave. Exactly duality of the class F power amplifier. Okay, we can also calculate the details. I'll skip the details, but just look at the drain efficiency, right? Just by observation, we know no overlap, so therefore 100% efficiency. Right. The last example I want to show you is this class D power amplifier. It is very widely used, kind of echo what Ali is talking about. And for the audio signal processing, Class D power amplifiers are widely used in the audio applications. Okay, so how does this work? A basic topology of Class D power amplifier is implemented by two switches, SWA and SWB in series. And they are being turned on and off in a non-overlapping fashion. And the output of the two switches will be connected to a series LC tank, and then with a load resistor. Okay, and of course, the upper side of the switch will go to VDD. And first of all, let's look at the waveform, right? So the switch A and B will be complementary to each other, so and then it's short to VDD. So if we look at the voltage and across switch A, look at across switch B, both of them has to be square wave 50% duty cycle and on-off from 0 to VDD, of course. What about the current? The current, because of the LC series network, first of all, only RF current can go through, and also only fundamental current can go through. All the harmonic current will be rejected because it cannot go through the LC series network. It's open circuit. So therefore, the current going through the load has to be a sine wave current. And looking at this sine wave current, we know this current needs to be provided by the switch, right? It cannot come from anywhere else. So therefore, we have to map the current. You can see that if the SWA is on, then it is providing the upper part of the current of the sine wave. If SWB is on, it's providing the lower part of the current. And the current going through here is exactly IA and minus IB. So IA minus IB equals IL, right? This is the simple KCL relationship. IA minus IB equals RL. So therefore, IA minus IB equals IL. This is the only solution if you have 50% duty cycle. Right. Again, some of the details, but we can see that, hey, if this is the voltage and the current waveform, if you look at the integration of the voltage and the current across the transistors, it's always 0. So therefore, the transistor itself consumes 0 power. All the power drawn from the supply will go to the load. So therefore, the efficiency is, again, 100%. Finally, let me summarize my talk. So the power amplifiers are playing a critical role in almost all the wireless systems, as we introduced. So the key metrics for PA designs include the output power, energy efficiency, linearity, bandwidth, and the form factor. And the power amplifier voltage and current waveforms will govern the PA output power and the efficiency, as we have seen through all these examples. As a result, power amplifier design is an art of waveform engineering. And as I mentioned earlier, the waveform engineering is a fundamental circuit concept, right? And widely used not only for PAs, but also in multipliers, VCOs, and DC and DC converters, for example. And there are different PA classes depending on the different biasing and passive network topologies. They are being used for different applications. Typically, linear PAs are more widely used for wireless communications, and the nonlinear switching PAs, they have higher efficiency, and they are often used for radar and sensing applications. If you want to get more information, feel free to check out the references and the resources. And yeah, thank you. Yeah, thank you for your time. At the end of my talk.
Thank you for the great talk.